Sorry for this delay. I think now everything is in order. What I would like to actually present to you is our latest findings and our latest algorithm that we have developed in the area of working with the asymmetric laminates and the prediction of their elastic coefficients. So this is something that's related to our several projects currently ongoing here. And the idea is actually to just address briefly the 4 steps that we have so far implemented in this area. This is again not working. Everything is not working. So just generally, I will skip this. It's compository general expansion, as we all know, but there are still quite a lot of things that we really need to solve if we actually master the science of composites as is. One of the problems, whatever you do, whether it's static or dynamic, at one point or another, you'll end up actually being in a need to find the elastic coefficients of that particular material, whether it's a 3D or a 2D, as basically composites are mostly used as a thin laminates. In this particular discussion, we are actually concerned about the in-plane shear modulus, since this is the most influential one when it comes to twisting prone applications, like in our from Department of Aerospace, and we deal quite a lot with actually fly-worthy structures. And as I said initially, we're mostly concentrate on the asymmetric laminates, which I believe and generally believe that they are underused generally, and that they theoretically hide the power that really needs to be unleashed. Why is that? Why we are not using them at their full potential? Because they're modeling, and we still have no adequate theories which can actually fully support their development. That's mostly because there is actually, as you see in asymmetric laminates and their stiffness, actually ABD metrics as we call it, coupling between the bending and the twisting exists, which is actually hard to predict depending on the fiber arrangements based on current theories. As I said, we believe that if nothing else, if we master the science of asymmetric laminates, we can gain quite a few benefits. One of those would be, of course, the lighter structures, which is in the aerospace quite advisable. So these are actually, when we talk about, they're actually four independent elastic coefficients within a stiffness matrix according to a generalized Hooke slope or orthotropic structures. And relatively for the asymmetric laminates are really hard to predict. Actually, at this stage, they have to be measured. So this is what we actually do. We have tried to deploy machine learning, and I will show you the complete steps and the final results of our algorithm, whether based on this we can actually gain some experience and actually some knowledge when working with asymmetric ones. We tried actually combining as it is a general roadmap in the machine learning, analytic models, experiments, and numerical simulations, just in order to create the data set. In this particular case, the data set actually contained about 200,000 combinations of the asymmetric. At this moment, we are actually concerned on the carbon ones, AS4, within the epoxy matrix. The second challenge was based when the data set was created, to recognize the most suitable algorithm for the train model recognition, to test those data and actually to deploy it within the software. This is actually a process not as straightforward like presented here, but rather process that is actually back and forth. You always recommend there's something wrong. Since, as I said, at this stage, and I'm presenting also due to a time constraints, that we are most concerned about the in-plane shear. This is actually a current standard, and as it is proposed for the composites, but I will tell you right away, I'm just showing you this since we simulated this test. Actually, first initially had to modify. The problem was, since the tests suggest this actually only works for so-called balanced laminates, which contain fiber orientation in 0 and 90. This was not satisfactory for the problem that we were trying to save, since we actually really needed to cover for all the angles between. So this is what actually we did. The problem when working with asymmetric laminates here, and why this test directly is not applicable, is since within the plies of an asymmetric laminates, your strain distribution is actually totally different from ply to ply, and you are actually measuring the strain only on the first ply as per standardized test. Let me just see if I skipped one here. So this is our simulation of the standardized test. However, with the change to accommodate the possibility of testing the asymmetric laminates, we are not actually measuring the strains, but rather we are measuring the displacements. To be more specific, the rotation of the central node of our model. The central one is actually coincide with the shear center, since the actually our test coupon is actually symmetric. So this gave us an insight to simulate actually this. Sorry, because this is in reverse here. To simulate this test, but with this modification. So we are not actually, and to accommodate to have all this possibility. So we are actually measuring the rotation of this particular coupon at this particular position, as I said, in a shear center, and then deploy actually the basic theory when it comes to shear stress with the formula. For the known force, geometry of the coupon and the rotation, we are in a possibility to determine the equivalent stress. So not this, but something like that. So we developed in order to gain a data set. The data set, as I said, contained quite a lot of entries, which is the case always when you're dealing with the machine learning. And this I'm just showing to see when you let actually our intermediate set for creation of data set creation, how actually it works, how fast it is. It's not fast at all, but you are actually doing this only once. So it was not something that was of concern. You just let it run. It randomizes the fiber orientations, calls the solver. In this case, FE solver was Nastran, and then the data set is actually created. And this is the schematics. On one side, what I have shown you is on the top, a part of a data set. Based on our previous experiences, we were actually targeting to use in the development of the machine learning actually algorithm, the regression algorithms, because they have proven to be very good in the problems like value recognition, which is one of actually these. Also, they are known that they work very good within the bounds that are given. So this is why to our asymmetric data set, but based on classical elimination theory, because it is much faster than the finite elements, added due to bounds symmetric ones, in terms they couldn't hurt. So actually our data is coming from two sources, FE simulations and basically the classical lamination theory, but as I said, for the reasons to bound the future regression algorithm. So based on this and our actually help routines that we have developed, the technologies that we worked on are from Astra and MATLAB, C programming, Python programming, and something that we generally use regularly. I mean, all of us these days. Also, these funny letters here, this is something due to a font, problems with the fonts, but it would say we randomized our data set and actually we checked for the anomalies as well. Again, something that's been done on a regular basis. So we ended here at the position that the question of the algorithm was to be answered. As I said, we targeted the regression algorithms, the technology that we work with, and also from our previous experiences in our other project. We like to work in these situations with ML.NET technologies, and basically first to investigate what kind of actually algorithm regression ones, and they're all listed here, would work best on our data set created as explained previously. The idea was to initially start them all and to let them run for a certain period of time until we, in the first pass, recognize the one that in the shortest amount of time gives us the highest R square. Of course, this particular one is low, but as I said, the first initial step was just to recognize which of those suggested regression models is the best candidate. Once we actually recognize it, we strike out the rest, and in this case, it LGBM, like GBM regression model to be, since as I said again, in the shortest amount of time, gave us a relatively high confidence level R squared value. When this was done, we let the machine run, but only with this particular algorithm, and the rest is just to implement our, as you can see, MLV2 model for this particular material system and for this particular elastic coefficient. Why inverse? When this was done, we were in a position to have in place the machine learning algorithm that can basically, based on the fiber arrangements, unsymmetrical one, predict the equivalent shear modulus of that particular system. Why inverse in this net? We wanted to go a step further just by not entering the arrangement, but rather to asking for a best optimal arrangement for that particular value, in terms that give me the shear modulus that you wish to obtain for your particular structure, and I will try to predict what kind of arrangement you should ask. So in this case, again, this is in real time. The only entry data is the desired shear modulus, and based on our ML algorithm, but in inverse, will obtain most likely the best solution. So if we look at actually 6.6 some are actually values that we work with, and actually the software, our inverse algorithm, gave us several possible layouts. Look at the first one. Oh, yeah, sorry. Look at this one. Now let's zoom. That's the very first, the asymmetric one. The thing that we actually, you see angles of 53, 57, 69, 90, minus 80. Nobody would have guessed that except for the ML algorithm. But the key is here in the volume fraction. The volume fraction of this 0.4. If we look at the classic symmetric layups, volume fraction is close to a 0.6. Basically, this is directly related to mass of the system. So I think this algorithm achieved this goal. And these are actually the problems that we are dealing with, that we will try to deploy this algorithm, mostly in the plate stability that we are dealing with in the realm of of air elasticity. And we're going towards, actually, and I'm finishing, basically to completing the complete stiffness matrix for a plane, thin structures. As you can see, we would need to incorporate E1, E2, and a Poisson ratio, major 1 and mu 1, 2. So we are actually working with that, starting from simulation and tests. But now, actually, since we've gained some experience using the shear modules and developing the whole system, as I have shown you, to deploy this for all other three elastic coefficients, and then to progress to working with the more complex structures, such as earlier mentioned, like, I don't know, sandwich structures with a core and also different materials. This one in order, the glass on the right and the Kevlar on the left, and this one was already tested. So that's all I have for a moment. Thank you very much.